Okay, so hello everyone. Today is our seventh short online conference, and we have two topics which will show us the usage of the GNSS data in the opportunistic sensing perspective. Anna, could you please introduce our today's speakers?
Yeah, the first speaker is Giovanna Venuti, and she's an associate professor of geomatics at the Politecnico di Milano. She is involved in studies that utilize GNSS data to detect water vapor variations associated with heavy rainfall events. And she also contributes to the integration of GNSS-derived products to high resolution numerical weather prediction models to further enhance the accuracy of rainfall forecast. So with this said, I would let the floor to Giovanna if you are ready to share your screen.
Yes, thank you, Anna, and thank you, everybody, and good morning. Thanks for inviting me to give this speech. Let me share my screen and sorry. Okay, let me know if you can see my presentation. Perfect. Okay. As I was saying, thank you everybody. Thank you, Roberto, for inviting me, for involving me in this meeting. I will talk about GNSS meteorology, which is the field in which I'm working with since I think 15 years. So the starting point for this presentation is GNSS ZTD. So the possibility to sense, to sound the atmospheric water vapor by means of what is called global navigation satellite system. Maybe some of you knows already about it, some others know. It is, maybe you are more familiar with the global positioning system, which is the United States system for positioning and navigation. GNSS is the acronym that includes all the different satellite system nowadays available in the world. So not only that from United States, but for instance, the European one, the Russian, the Japanese, Chinese one, and the Indian one. What is this system and how it can be used for meteorological purposes? This is the topic. GNSS is a satellite system. It means that we know, so it is based on the possibility on the fact that a satellite constellation, well, more than one constellation, are able to establish a global reference system. You can imagine a Cartesian coordinate system, Earth-centered and Earth-fixed, in which the position of the satellite is known. You know their coordinates as they are orbiting at 20,000 kilometers far from the Earth's surface. You know their position, and if you are equipped with a proper receiver, a GNSS receiver, you can track these satellites, the signals emitted from those satellites, and you can determine your own coordinates in this global framework, wherever you are on the globe. This means that it is global. You can determine your position even if you are moving. So it's also a navigation system. It was born for navigation purposes, as a matter of fact. This is done by trilateration. So if you are able to track to at least 3 satellites, well, more than 3, at least 4, because you have to account for some errors. if you are able, in principle, to track 3 satellites and detect and determine and measure the distance to those satellites, you can write a system of 3 equations in the 3 unknowns that are your coordinates, solve the system and determine your position. This is done instantaneously. Let's say it is possible to do this positioning while you are moving, and in a continuous, let's say, way. But how can you measure the distance with respect to the satellites, to this reference point? Well, this is done by means of the GNSS, of an electromagnetic signal that is sent by the satellites in the constellation. This signal is received and properly processed in the receiver, and to determine the time it takes to the signal itself to cover the satellite, each satellite receiver distance. If you multiply this time, okay, you have also always to have in mind that we have to manage a lot of systematic errors, but I will not mention them here, but because we can manage to remove them. Well, if you have this time, you can multiply this time by the velocity of propagation of the light in vacuum, which is known, to obtain what is called the optical distance. Well, this distance is not let's say, the geometric distance between the satellite and the receiver, because as a matter of fact, the signal is not propagating in vacuum. It is interacting with the Earth atmosphere, and the effect of this interaction is a change in the propagation velocity. So we have to account of this change in the processing of our GNSS observations if we want to get accurate positioning. And how we account for this? Well, we introduce in all the observation equations, in all the distances, the fact that, okay, the optical distance that we measure is after correction of some errors, the geometrical distance plus an extra path, and this extra path is called delay or slant delay, because it is in the direction of the line of sight of the satellite, and it is exactly the difference between the first term is the optical distance and the true distance, the actual distance, the ones that would result from the knowledge of the true velocity of propagation of the light through the atmosphere. This extra path can be expressed in terms of, so it's the integral effect along the path of this change in the velocity, and it is why we can use GNSS, because this change is due to the gases in the atmosphere, to the we will see, to both the ionized gases in the ionosphere and the other gases in the troposphere, but this cumulative effect can be, as a matter of fact, determined in the GNSS processing. Well, this delay, which is linked to the refraction index, can be split into the delay due to the ionosphere, the interaction in the ionosphere and in the troposphere. For what concerns this presentation, we just say that we can separate the two contributions, and here we concentrate on the effect due to the interaction with the troposphere. This is what is interesting for meteorological purposes. So it is the integral of just the component of the refractivity index along the path, but just for the tropospheric component. Well, as I was saying at the beginning, we observe something and then we have to process the observation to get the position of the points. And now we have introduced in our observation some additional parameters that we have to estimate in order to get accurate positions. But we cannot, as a matter of fact, determine all the different length delays too much. So in order to obtain our position, we have to reduce the number of parameters, and this is done by projecting the delays affecting each satellite signal, so along each different trajectory onto a common delay, which is the delay in the zenithal direction above the receiver. So imagine that in a certain epoch, you can track a number of satellites, 10, 15 satellites. If you exploit different constellation, for instance, you can write a system of n equations, as many as the number of satellites that you are simultaneously looking at. And in these equations, you solve for some parameters that are to correct some errors. You solve for the position of the receiver, which is a unique unknown, and 3 unknowns, and for this common zenith total delay. I stress this fact because the GNSS is an opportunistic measure of water vapor, but it is not a direct measure. Is obtained from the post-processing of GNSS observations. It is a cumulated parameter, and it is also an average parameter because, as a matter of fact, it includes what the signal to different satellites are recording about the status of the troposphere. The other point is that this parameter, so what is the advantage of using GNSS? Well, the advantage is that GNSS stations are already there. You don't need to install new stations, but there are networks of GNSS receivers that are installed for and operated for geodetic purposes. Or surveying purposes. You see here on the right, on the upper right, the black areas are the points where you have GNSS stations. For instance, this is almost all black in the United States, in Europe, in Japan, because the networks there are very dense. So this gives you an idea of what is the spatial sampling of the atmosphere that we can obtain from existing infrastructure. And this ranges from 10 kilometers to 15 kilometers in Europe, 10 kilometers in Japan, in North America. The point is that this is not even distributed. These networks are completely, for instance, missing in Africa, or there are networks, but they are not making the data available for free and continuously. They are not guaranteed. This is the situation in Italy. This is something that I already said. So it's not GNSS ZTD. So it's available, is there. It is something that can be obtained by the processing of data that are already collected, but it requires time. It is not an instantaneous, so it's not, it requires some latency due to the processing, not only the processing, but also the availability of, for instance, the satellite coordinates that are not immediate. So we are the possibility to have near real-time ZTDs, but near real-time means after 1 hour or maybe less, but they are, in some cases, there are more errors, they are less accurate. Well, this is just to say that the ZTD can be again subdivided into the contribution of hydrostatic gas and the water vapor only, and that the component that is related to water vapor can be can be expressed in terms of precipitable water vapor. Maybe you are familiar with this, more familiar with this variable. It is the depth of rain resulting from the condensation of the water vapor in a column, in a vertical column over a given point. And this is linked to the wet component of the Z delay by a coefficient that is in the order of 1/6. What is the accuracy of the GNSS ZTDs? Well, we can assess this accuracy by comparing, for instance, the GNSS observation with the radiosondes delays. From radiosondes data, meteorological data, you can determine, so pressure, temperatures along the path of the radiosondes, you can derive the refractivity index, and by numerically integrating the refractivity index along the path of the radiosondes, you can derive either zenith wet delay or PVV. And you can compare it with close by GNSS receivers. And this comparison tells us that the accuracy, the standard deviation, let's say, of the differences is in the order of 2 millimeters. 2 millimeters means 1.2 centimeters in ZTD, and the signal power of this ZTD is in the order of that wet delay is in the order of decimeters, while the total delay is in the order of meters. And now some applications. I know that I have not much time more, but I want to mention some application that we of ZTDs. Let me just say that we cooperate with our spin-off GRED that is able, that is, well, they process all the data usually, and we use our own GNSS ZTDs from available data, raw data from the existing geodetic networks, or networks of low-cost receivers ad hoc installed for experiments, for making experiments, because those low-cost receivers can densify the existing network. So we are trying to see if it is possible a higher resolution in the sounding of the atmosphere. So you can use the ZTD that you derive from existing network of GNSS receivers to produce water vapor or delay maps. Those delay maps, we have just developed our own strategies, starting from an existing methodology, but we have implemented it and let's say improved it, and we have improved it for the use with GNSS data only, let's say, because you can obtain those maps also starting from, for instance, delays computed out from numerical weather prediction models. Anyway, you can derive those maps. They are important for instance, for the intercalibration with SAR mission data. SAR, synthetic aperture radar data, can provide also a sounding of the atmosphere with different characteristics, and it is important, this intercalibration with GNSS, because the two systems use the same kind of signals in the same band, so they are affected by similar behavior, and one technology can be used to correct the other one. Another application that we have worked in the past, and we are still working in a project that is currently ongoing, is the use of GNSS together with the standard meteorological observations and the radar observations to detect the occurrence of convective rains. This means that okay, GNSS alone cannot be used to, is not sufficient to detect those phenomena, but it can improve the prediction. So this project was done in an area very small in Lombardy region in Italy. In the northern part of Italy, we have a smaller area which is prone to convective rains and to flooding. So it is an area where it is important to have this prediction of convective storms. And what we did is to train neural networks to with meteorological data and GNSS to predict the occurrence of GNSS data of these phenomena in the area of interest, where the occurrence, so there is or there is not, is based on the presence of observed convective cell by radar. Those radar data came from the Meteo Suisse. Well, the results were promising. We had, let's say, an overall accuracy of, this is a classification network. We predict if there is or there is not, but the frequency of the correct prediction is something like 87%. And okay, there is no time to discuss about this network, but if you want more detail, we can discuss it. We have done also a different job that is related to the possibility to predict the trajectory of the convective cell. This is a job that was done between the LAMPO project and the new project that is going on in this period. So we based our prediction only on the radar images. So we have we know that there is a convective cell in a certain area, and we want to predict where it will move in future. What we are currently trying to do is to first of all to predict rain, and predict rain based on the radar data and the standard meteorological data and rain itself. How? When there is a cell, so we know that the convective convective phenomena is occurring. Well, we consider for that position, so we have the position of that cell from radar. We can consider all the stations around, the meteorological stations around in a certain area, in a certain window. We decide to consider the 3 nearest stations. We use all the data of those stations and of all the GNSS stations available, the 3 nearest GNSS stations available around that point. We use the same data from the radar to train a neural network to predict the rain on the different rain gauges that we are considering. And okay, this is one point. The other point is of the ICREN project is to try to use the GNSS data also to feed a numerical weather prediction model, so to assimilate those data into numerical weather prediction model, and also the lightning data to see, okay, what is the improvement due to these observations when they are used to force the numerical weather prediction model. And then the final goal is that of comparing the 2 predictions, one obtained of rain predict from neural network, the other from a physical based model, and also to integrate possibly these 2 kind of predictions. And this is something that we are working on. The results that we had, okay, this is the area, these are all the different data that we are using. But the fact is that if you rely only on the neural network to predict rain, well, it is a very hard task. But in 10 minutes after the observation, okay, we predict, well, here where the rain is and also the amount. But if we go after 1 hour, then we can still predict where the rain is, but we underestimate the rain. So we are trying to improve this prediction, and with this I will finish this presentation. There are some references for you, and I'm available for questions.
Thank you very much, Giovanna. This was very interesting. So, is any question to Giovanna from our audience? So maybe I will ask the question, because you said that you are assimilating also the results from this ICREN project,
Yes.
right? So what is exactly the output which you are assimilating? I
The
mean, do
output
you have
that
the rain intensity, or do you have?
No, what we assimilate is directly the ZTD.
ZTD, okay.
The ZTD. It is possible to assimilate also the PVV, but it is not a good idea, because in order to pass from what we estimate from GNSS to pass to the PVV, we have to use the data, ancillary data, temperature, pressure on the surface, and those data are not really usually collocated. So the meteorological stations are not collocated with GNSS stations. So you introduce some error. So it is better that the numerical weather prediction does the job of passing, of just ingesting directly what you can provide.
Okay, so you have ZTDs from your GNSS stations, and you have also ZTDs from the neural network as the output.
No, from the output of the neural network is the amount of rain, as a matter of fact, in certain position, because we predict the amount of rain in the station, in the rain gauge that we use for training. And the integration which I was referring to is the use of the output, because the point is that the model the numerical weather model is able to see a much, let's say, a larger behavior of the convective rain, while we are focalized in a small area, and we are not even able to interpret with mostly due to the fact that we have yes, a lot of data, 10 years of data, but in any case it's still a poor data set, because the occurrence of this convective storm is not so high. Okay, you have not heavy rain, you have daily rain, heavy rain, but the point is that you can use the model to predict, for instance, after 6 hours the situation, based on the physics of the atmosphere, because this is what happens with the model. And then the network is able to advance very, very fast, very quickly. And so you can gain some more time by using the output of the model to go farther in time. And so what we are trying to do is to see if the model, we are trying to get from the model the same observation that we can get from the rain gauge and from the meteorological stations. The point is that we are not able to produce a data set for the training of the network, which is let's say, large enough to have good predictions from numerical weather prediction simulation, because it's too heavy. So we assimilate the data in the system, we produce our best prediction with the model, but then we use from the model the we predict from the model output the meteorological variable in the position of the existing stations. This is what we are going to do. And we are going also to predict the radar observations, because the radar observations gives us the exact position, well, the position of the convective rain phenomenon. So where the radar attenuation is above a certain threshold, you say, okay, there in that area, you have this attenuation and you have a convective phenomenon. So we can start from them to consider the area around and the stations around where to make the training of the neural network.
Thank you, Giovanna, for all these explanations. Here is also the question in the chat. Is there available the public data set?
The data sets, they are not public in the sense that we have it, we can share it if you ask. In the past, we have made it public within a certain project, but I don't know if they are still available now. Anyway, the raw data are available. We are okay, sorry, the ZTD values, we have them. We can share them. We can agree on sharing the data, and at the moment they are not public available because they are not even used in Italy. I forgot to mention the fact that ZTDs are operationally assimilated in many. Christina will tell about this probably after in Europe or in America, in Japan, but in Italy we don't. We compute those values and we get rid of them. They are errors. We don't care about them, but they are useful as a matter of fact. And so this is not operational in Italy at the moment, let's say. So we have those data. We can provide them if on request for free, but we need to. But it is not. We don't have a place where they are published for the moment.
Okay, and the last question in the chat is, I am not sure I understood correctly, the data latency is between 1 hour and 1 week, right?
I wrote this because it depends on the accuracy. If you are interested, for instance, to calibrate SAR data to correct the atmospheric effect in other EO mission, then the 1 hour latency is not important. You can even go for a more accurate estimate of ZTDs, and this happens after, I would say, 1 week, because 1 week is the time it takes to the global satellite system, GNSS, service to release the precise position of the satellites, what are called the precise ephemeris. But there are very let's say ephemeris that are given after 1 hour that are very accurate nowadays. So we can use them to make this less than 1 hour that can be used. There are also the predicted orbits, but they are not enough accurate for our purposes.
Thank you, Giovanna, once again for the presentation and for all the answers. And it is time now to move to our second presentation.
Yeah, our second speaker is Cristina Oikonomou. She is a researcher at Frederick Research Center in Cyprus and director of Cloudwater, which is a startup focusing on development of low-cost sensor GNSS and receivers. And her research interests are ionospheric and tropospheric physics and their interaction with the GNSS. And within the OpenSense action, she is a member of working group 3 and 4. And with this said, Christina, can you share your screen?
Yes.
Ready?
Hello, Anna. Hello, everyone. So let me share my screen. And so you can see my screen. Is it okay?
Yes, perfect. Thank you.
Thank you. So good morning from me. I'm Cristina, and I also want to thank you, Roberto Nebuloni and the COSTAXON for this invitation today. So our group, the last 16 years, is working on ionosphere by having installed a ionospheric radar and GNSS network in Cyprus. But the last 6 years, we are also doing research on troposphere and GNSS meteorology. So you'll know during the last about 25 years, the number of extreme weather events has increased dramatically due to climate change. And one example is very recently in Valencia region in Spain. And these events have caused thousands of deaths and economic losses. Another similar event was last year that caused large flooding in Greece and Libya at the Daniel storm. The Daniel storm turned to a medican. What is a medican? Medican is named as the Mediterranean hurricane. It is a tropical-like cyclone that is created on Mediterranean Sea, and it was firstly identified during the 80s. But with reanalysis, past reanalysis data and recent satellite data, we have managed to identify around 100 medicants since the 50s. And there is ongoing research about their characteristics and also how they are affected by the climate change. One example is the coast action med cyclones, the very recent coast action. So Daniel Medican was created south of Italy at the central Mediterranean and moved eastward towards Libya, but didn't affect Cyprus. But another Medican 3 years ago, Apollon, had a similar orbit. It was initiated again south of Italy in central Mediterranean Sea and moved eastward, also affecting Cyprus and reaching Turkey. Mediterranean Sea also faces recently very rapid warming of the temperature. There's a sea surface temperature rise, and particularly this rise is very intense, as you can see at the Eastern Mediterranean region. So the Eastern Mediterranean region in terms of climate change has been identified as a hotspot. Particularly Cyprus region is identified as a hotspot mainly for heat waves and dust storm events. As you can see here, we have a problem from dust coming from Syria. But the last year, we also faced extreme events, precipitation events that have caused flooding. And this was reflected last year. There was a flooding at the eastern part of Cyprus. And there was an unusual trajectory of the storm that from the east that could not be predicted by the numerical weather prediction models. Also, we have an increase in lightning and tornado activity the last 5 years. This is the severe dust storm event that initiated from Middle East and moved towards Cyprus within 6 days, as you can see. We also face severe dust events from Sahara dust from Africa. The dust particles reached to height of 3.5 kilometers, and the visibility in Cyprus, particularly in Limassol, was decreased to 300 meters approximately. So as it was obvious from Giovanna's presentation and these extreme events, there is a need to improve nowcasting of weather. And one way, and we need actually to improve the traditional forecasting systems, and we need to combine data from ground and space data, satellite data, also opportunistic sensor data with higher density and higher spatial resolution. One example, it is the water vapor and precipitable water vapor, which currently is used by approximately 17 national meteorological services in Europe, that they do assimilate precipitable water vapor operationally Japan has started firstly many years ago. Also USA, Met Office, and in UK and France. But in Cyprus, we don't have this capability. Water vapor, as explained by Giovanna, is estimated by exploiting the tropospheric delay of the signals coming from the GNSS satellite to the ground. The first initial effort to exploit water vapor from GNSS geodetic receiver was initiated approximately 20 years ago by the UMETNet program and through this cost action. And as you can see here, within 20 years, the network of the GNSS receiver is increased a lot, but there is a gap on the eastern part of the European Union. So to meet this gap, our group initiated an Interreg project, BERTIS, to install a real-time water vapor service that will provide water vapor in Greece, Bulgaria, and Cyprus. Because the geodetic receivers were very expensive, approximately 13,000 euros, in Cyprus we were able to install only 2 receivers. So the BERTIS network is now operationally. Here you can see the new meteorological and GNSS stations in the 3 countries. And the data are available in this website. You just have to send me an email and we can provide the data. They are actually water vapor, ZTD, and gradients in a 10-minute resolution. They are updated every 10 minutes, and we start to provide this data since 2020. This is a high-grade geodetic receiver. And we very quickly identified that you cannot build a dense network of receivers to exploit the water vapor because they are very costly. And so we managed to take funding from the National Research Foundation and to install a startup company, Cloudwater, which aims to build a low-cost GNSS receiver. So this receiver is built using 3D printing, and it costs around 2,000 euros. So our plan is to densify the network in Cyprus. Firstly, we have validated the low-cost receiver in Kliru station in Nicosia by collocating with a high-grade Leica receiver and by using the same Vaisala meteor sensor and the collocated Leica antenna. For 3 months here, October, November, and December 2022, you can see that there is a very high correlation coefficient between the high grade and the low cost GNSS receiver, both for ZTD and for water vapor. So here is the current network that we operate, and they are the technical characteristic of the receivers. So we aim to densify the network, not only Cyprus, but also at the capital city of Nicosia. And we want to build low-cost receivers with a distance between them about 5 kilometers in order to increase the accuracy and the information of water vapor within the cloud, and to use them for nowcasting actually. So currently the Department of Meteorology in Cyprus is operating 2 weather radars at Larnaca and Paphos airports close to them, a radio sonde at the capital city Nicosia, and it has also about 100 weather stations that they provide meteorological observations. Here you can see the radar images that are produced simultaneously from the X-band Doppler dual-polarization radars. And these data are available from this website, also the latest images. The radar provides the reflectivity in copy mosaic and the Doppler velocity. The copy mosaic scanner layer is 2 kilometers. And the images are updated every 10 minutes. The radio sonde at the capital city, it provides measurements only at 6 and 12 UTC time, and we have data since 1981. But there is the problem with the Cyprus Department of Meteorology was that they don't use and they don't have a lighting a network and they don't have wind profiles. They don't use water vapor, ZTD into their models and no other space-based observations because they don't have permission to use also EUMETSAT satellite products. And also, they do not assimilate their data into the numerical weather prediction model that they use, which is WRF. So sometimes they provide false warnings of extreme events. So taking this in mind, we had a recent strategic infrastructure project, which is a collaboration with the Department of Meteorology, Frederick University and Research Center, and Cloudwater, and also the National Observatory of Athens is participating, and 9 municipalities in Nicosia. So it's a collaboration between academy and the industry, and we aim to enhance and to enrich the existing meteorological infrastructure of the Met Service by installing a lighting detection network system accompanied with a radar wind profiler at Larnaca Airport and a microwave radiometer collocated with the radiosonde, and also to densify the GNSS network. All this data will be assimilated in WRF model, which now the department has not this capability because of the cost and also they are understaffed. So this is here in the capital city, you can see, which is an area of 25 square kilometers. We aim to build 9 receivers. At the moment, we have 3. And this network, hyperdense network here at the capital, it will be augmented by microwave radiometer to measure the temperature and water vapor profiles with high accuracy. We are now in the tendering processing. We have initiated this. So the existing system of Met service in Cyprus with the 2 radars will be augmented not only by the microwave radiometer, but also with the radar wind profiler here at Larnaca Airport. The radar wind profiler that we are also now in the tendering process will give accurate and wind profiles and also the wind shear in real time, which is very useful for Larnaca Airport and for nowcasting and for the Met service, but also it will be used for research by our group to study the boundary layer and also the dust severe storm event. And finally, the lighting detection network system that we are also in the tendering processing, we aim to install 5 antennas, which is a very high resolution for Cyprus Island, and to give in real time to the Met service the occurrence of flash and strikes. So this is the overview of the system that we are building in the frame of this segment project. To enhance the existing meteorological infrastructure of the department, but also to enhance our research activity. And it's not only the observational system, but the fact that this data that come from this system for the first time will be assimilated to WRF numerical model, and they will be used to improve the forecasting services of the meteorological service. Another activity that is going also to finish in February is a European Space Agency project that we coordinate, and we are conducting an experiment, an assimilation experiment only of ZTD into WRF model over Cyprus. And a future possibility is to use not only the tropospheric capability of the GNSS network to provide water vapor, but also to provide electron content and to monitor ionosphere, particularly now that we are at the we have high solar activity from the sun, and we expect many solar storms and ionospheric disturbances. Thank you very much. Thank you.
Thank you, Christina. This was the amazing presentation, which is showing how many things one can get from the GNSS data. And it's very nice to see that all these different aspects of GNSS data usage are so advanced in Cyprus now. Is it any question from the audience?
I would have a question. You hear me?
Yes.
Yes.
So George from Luxembourg. Are you using, in addition, personal weather stations? Because you could validate some stuff via personal weather stations. And in the OpenSense action, there's a lot of activity going on to migrate, or not migrate, but combine data from weather stations, official ones, personal weather station, and other kind of opportunistic sensing to augment the information that is available. I'm not sure how many of these personal weather stations would be available in Cyprus, but there are for sure some.
Actually, to tell you the truth, there are not personal weather station network in Cyprus.
Okay.
We have not developed this aspect. But there is a dense network of meteorological stations and automatic also. And because Cyprus is a small island, and until now, there's no interest about personal weather stations that it would be really helpful, yes.
Is it any other question to Christina?
Then in the same term, do you use microwave links or have you investigate this? Because it's the same. OpenSense does also use a lot of methods using microwave links. So like from phone providers in Cyprus to have an additional information or an additional density in the network.
We have contacted the national telecommunication company to make an effort and convince them to share these links, but they are not. They don't want to spend time on this, and there is no regulation actually how to share this data. But we will try again to contact them to convince them. And I don't know if Haris Haralambos, who is the head of the group and has made contact with the CETA telecommunication system, Harry, you want to say more details on this contacts that you did and this effort?
Yeah, unfortunately, they are not really interested. And we are trying to press them with respect to their social responsibility in order to share some data, but it's an ongoing process, not yet fully developed, I'm afraid.
But we have these other satellite links, communication links, SMLs in Cyprus.
Yeah, we're trying to exploit or to evaluate the probability, the chance to exploit a couple of links used, SML links, and we are in the process of reaching an agreement and trying to evaluate this kind of data. That's true.
Okay, thank you.
Thank you, thank you.
Do we have any other question to Christina? If not, I am sure that Christina will be willing to answer you per email, or you can always contact her via Zulip if you are in the OpenSense community. So with this, I would like to thank you for joining today's meeting. And announce already the next conference which is scheduled on January 28th at 9 o'clock. So thank you very much. Thank you,
Natalia. Thank you very much. Thank you. Bye.
Thank you. Bye-bye.
Bye-bye.
Thank you also from my side. Bye-bye.
Bye, everyone.
Thank you, Cristina.